For almost a century, the global helium market had a massive shock absorber built into it, the U.S. Federal Helium Reserve in Amarillo, Texas.
I find it wild that the U.S. government was just hoarding gas in an underground cave in Texas.
I mean, it started back in the 1920s. The military thought the future of warfare was giant dirigibles, blimps. They needed a lifting gas that wouldn't explode like the hydrogen in the Hindenburg. So they started stockpiling helium in a naturally occurring geological dome in Amarillo. And after blimps became obsolete, the space race and the Cold War kept the demand high for rocketry.
So they just kept filling the cave.
Yeah, for decades, this reserve supplied over 50% of the world's demand. Because it was government-run, it sold helium at artificially subsidized, predictable prices. It was a de facto price floor and a massive supply buffer.
But then the government decided they didn't want to be in the gas station business anymore.
Exactly. Congress passed the Helium Privatization Act in the late 90s, mandating that the reserve sell off its inventory and shut down. That sell-off finally reached its cliff edge in 2021.
Wow, just a few years ago.
Right. The reserve began winding down operations, effectively removing the world's largest safety net.
They just turned off the tap.
They did, and this created a massive structural supply shock right at the exact moment in human history when demand began going exponential.
Because of tech.
Exactly. We had the semiconductor fabs scaling up, driven heavily by massive government investments like the Cheech FPS Act. We have the nascent but incredibly resource-intensive quantum computing sector.
Yeah.
And most urgently, we have the artificial intelligence infrastructure boom.
And the craziest part of the white paper is the waste. The data shows that current global helium consumption is about 6 billion cubic feet per year. But roughly 20 to 30% of this is just wasted.
Just gone.
Gone. It's vented into the sky, it leaks out of microscopic cracks, it is lost during routine maintenance.
Which is a catastrophic inefficiency for a resource that takes 1 million years to bake inside a rock.
Totally. So let's focus on the AI part of this, because that is where the most urgent helium recovery opportunity lies. Why do AI data centers care so much about a gas that makes balloons float?
Well, to understand this, we have to talk about the physical limits of thermodynamics and heat.
Right. If you look at the NVIDIA GPU roadmap detailed in the sources, the thermal output of these artificial intelligence chips isn't just growing, it's going vertical.
Oh, absolutely vertical.
Back in 2022, we had the A100 chips. A full server rack of those ran at about 25 kilowatts of power. And at 25 kilowatts, you can still use advanced air cooling, right?
Yeah, you essentially just build a very sophisticated, very loud fan system to blow deeply chilled air over the metal heat sinks as fast as physically possible.
And even at 25 kilowatts, the acoustic trauma inside those data halls from the fans is intense. But air has fundamental physical limitations.
It does.
Because fast forward to the Blackwell generation rolling out around 2025, and those racks are pulling 130 to 132 kilowatts per rack. And the projected next-gen chips, looking toward 2028, they're forecasting upwards of 1,000+ kilowatts for a single rack of servers.
Yeah, the white paper states point blank that standard air cooling becomes physically impossible to manage above 60 to 80 kilowatts per rack.
It just fails.
Completely. It doesn't matter if you build a jet engine to blow the air. It just can't rip the heat away from the copper bus bars and the silicon fast enough.
So we have to look at the underlying physics of why air fails here.
It comes down to two properties: thermal conductivity and specific heat capacity. Air is mostly nitrogen and oxygen. Its thermal conductivity is roughly 0.024 watts per meter Kelvin. That is quite low.
Okay.
When you push a server rack past 60 kilowatts, the air simply cannot absorb and transport the thermal energy fast enough. The air right next to the silicon gets superheated, and instead of carrying the heat away, it starts acting almost like an insulating blanket.
Oh, wow. So it traps the heat.
Exactly. This causes thermal runaway. You get hotspot instability, the silicon degrades, calculations fail, and eventually the processor destroys itself.
Enter helium, the invisible hero of the thermal management world.
Yes. The physical properties of helium are uniquely, almost perfectly suited to solve this bottleneck. Its thermal conductivity is 0.152 watts per meter Kelvin.
So that's what?
That is 6.3 times better than atmospheric air.
That's huge.
On top of that, its specific heat capacity, which is the absolute amount of thermal energy it can carry per kilogram of mass, is 5.2 times greater than air.
Okay, so if I'm visualizing this, using air is like trying to wipe up a massive water spill with a cheap, thin paper towel. It gets saturated immediately and just pushes the water around.
Right.
Switching to helium is like dropping a massive, hyper-absorbent commercial sponge onto the spill. It just pulls the heat into itself instantaneously.
That captures the thermal capacity beautifully, yeah. But there is a second mechanical advantage that is just as critical for a data center.
What's that?
Dynamic viscosity. Helium's dynamic viscosity is significantly lower than air. A data center rack is an incredibly dense, tight space. Trying to shove air through those tiny gaps requires massive mechanical force,
Which means massive fans.
drawing huge amounts of electricity. Because helium has such low dynamic viscosity, It encounters far less friction. You can push vastly more of it much faster through the same tight spaces while using massively less power for the circulation fans.
Which is a huge double win. I mean, you get way better cooling and you slash the electricity bill for the cooling system, which in a hyperscale campus is a massive part of their overhead.
It's essential.
So the solution seems obvious, right? Seal the server halls, pump them completely full of helium, and let the gas do the heavy lifting. But the white paper highlights a massive vulnerability here, a phenomenon they call the bleed.
Yeah, this is where the physical reality of helium turns against the operator.
Right. The white paper models a standard 100-megawatt hyperscale AI campus. When they seal the halls and cool with helium, they are losing 5 to 15% of their total helium volume annually.
And that's just the baseline.
Right, just from ambient leaks, routine maintenance cycles, and outgassing. We are talking about venting hundreds of thousands, if not millions of dollars, straight through the roof every single year.
And we must note that the 5 to 15% figure is just the baseline leakage from imperfect seals. I mean, a data center isn't a static tomb. Technicians have to enter, servers fail and need to be swapped, upgrades happen.
People have to open the doors.
Exactly. When you factor in the open exhaust venting that occurs during those mandatory maintenance protocols, that volume loss can easily multiply by 2 to 4 times.
I can imagine someone listening and wondering, well, if it's just gas inside a sealed metal room, why is it leaking at all? Just use better caulk. But it's not that simple, is it? We aren't talking about trying to hold water in a bucket.
Not at all. The kinetic diameter of a helium atom is unimaginably small. It's about 2.6 angstroms, or 0.26 nanometers.
Which is tiny.
Standard industrial sealing techniques, rubber O-rings, silicone sealants, metal-to-metal joints, polymer gaskets, they look solid to the naked eye. But at the atomic level, they are full of microscopic voids.
So to a helium atom.
To a helium atom, a standard rubber gasket looks like a porous sponge. Through a process of diffusion, the helium atoms simply vibrate their way through the physical barriers we erect. Over time, they permeate right through the solid materials.
That is wild. So we have an artificial intelligence industry that is driving the future of the global economy. It absolutely needs helium to survive the extreme heat of its own computation. And yet the very nature of the gas means they are constantly bleeding this incredibly expensive finite resource into space.
It's a massive problem.
How on earth do we stop it? How do we catch something that can phase through solid rubber?
Well, that brings us to the core of the HelioGraph solution. And it's a massive technological leap. Using graphene as a magic sieve compared to the nightmare of conventional separation tech.
So explain how graphene membranes specifically improve gas separation compared to traditional cryogenic distillation, because I think we need to look at how industry has historically separated helium from other gases first.
Right. For decades, the only viable method has been cryogenic distillation.
Which means freezing it.
Yes, but freezing barely captures the extremity of the process. You have to take the mixed gas stream and compress it, then rapidly expand it over and over using turbo expanders.
Leveraging the Joule-Thomson effect, right?
Exactly, to pull the thermal energy out. You have to cool the gas down to below negative 196 degrees Celsius.
Wait, negative 196 degrees? That's insane.
It is. At that extreme temperature, the nitrogen and the oxygen in the mixture physically turn into liquids or solids and drop out of the stream. Only the helium, which doesn't liquefy until negative 269 degrees Celsius, remains a gas.
That sounds like it takes an unbelievable amount of energy.
The thermodynamics are brutal. It requires immense electrical power to run the compressors, massive capital expenditure to build the cryogenic towers, and enormous scale to be even slightly economical. You typically need feed rates of over 1 million standard cubic feet per day to justify turning the machine on.
So you obviously can't just park a massive industrial liquid nitrogen factory next to the server racks of a clean AI data center.
No, it's totally impractical.
Right. So HelioGraph completely abandons temperature. Instead, they use graphene. Let's look at the physical specs of this material. Graphene is exactly 0.335 nanometers thick. It is a single two-dimensional layer of carbon atoms arranged in a hexagonal lattice.
And the engineering breakthrough here isn't just using graphene, it's how they modify it. A perfect sheet of graphene is actually impermeable. Nothing gets through the hexagonal rings.
Really?
Yeah. So they bombard it to create engineered nanopores, literal microscopic holes that are painstakingly calibrated to be between 0.30 and 0.50 nanometers wide.
Okay, let's look at the geometry of this. The hole they punch is, let's say, 0.30 nanometers wide. And we mentioned earlier that the helium atom's kinetic diameter is 2.6 angstroms, which translates to 0.26 nanometers.
Which means the helium atom is smaller than the pore. It fits perfectly. It passes through these engineered pores via a mechanism called Knudsen diffusion.
Okay, I want to make sure I'm visualizing Knudsen diffusion correctly because the technical term sounds intimidating. A lot of people might just think of it like a bouncer at a nightclub letting small people in and blocking tall people, but that feels too anthropomorphic. It's more structural than that, right?
You're hitting on the core problem with that analogy. It's entirely structural. Think of Knudsen diffusion not as a conscious sorting process, but as geometric inevitability.
Okay.
Imagine you are standing in front of a heavy chain-link fence. In one hand, you have a golf ball, and in another, a large volleyball. If you throw the golf ball, it flies straight through the holes in the fence without even touching the metal wire.
And that is the helium.
That is the helium. But if you throw the volleyball, it physically smacks into the wire and bounces back.
Yeah.
It cannot fit. That is the nitrogen, which has a diameter of 3.64 angstroms, or the oxygen at 3.46 angstroms. They are physically, geometrically larger than the 0.30 nanometer hole.
That makes total sense.
The graphene is the chain-link fence. It is pure size exclusion at the atomic level.
I love that analogy. It's just dumb physical geometry. But if it's just about hole size, explain the molecular sieve mechanics and how graphene outperforms conventional polymers in selectivity. Why haven't we been doing this with regular plastic or polymer filters for decades? Why do we need the wonder material?
Because conventional polymer membranes don't operate on simple Knudsen diffusion like a single-layer fence.
Yeah.
They rely on gas solubility and diffusion through a thick, dense matrix.
Okay.
Imagine trying to push water through a thick brick of clay. The water eventually gets through, but the clay is thick, so the flow rate is incredibly slow. Because polymers are thick, the gas takes a long time to travel from one side to the other. In industry terms, they have very low permeance.
Right.
To process a large volume of gas, you would need massive warehouse-sized surface areas of polymer membranes.
Whereas the graphene is one atom thick. It's not a brick of clay. It's an ultra-thin coffee filter. The gas just pops right through the other side instantly.
Exactly the right framing. Pure graphene achieves extraordinary permanence.
Okay.
The white paper documents lab tests reaching up to 20,100 gas permeation units, or GPUs.
Wow.
And the selectivity, the ratio of helium that makes it through compared to the nitrogen that gets blocked ranges between 20 and 80. It vastly outperforms polymers.
But I'm reading the critical risks section of the roadmap here, and there's a massive catch. Making a pure, single-atom thick sheet of graphene perfectly at a commercial scale of hundreds of square meters without a single microscopic tear or defect is basically impossible right now.
It is incredibly difficult.
And if you have a microscopic tear in your chain link fence...
The volleyballs get through, the nitrogen and oxygen rush through the tear, and you lose all selectivity. You're back to a contaminated gas stream.
Right. So how do they actually build this if perfect graphene is a myth?
This is where HelioGraph's pragmatic engineering approach shines. They don't try to manufacture perfect, pure graphene. Instead, they utilize a hybrid composite architecture.
A hybrid.
Yes. They start with a very cheap, commercially proven polymer support layer, something like polysulfone, which is sturdy and porous. Then, they coat that polymer with a selective layer of nanoporous graphene oxide, or NPGO. This coating is slightly thicker, between 5 and 20 nanometers.
So they're layering the magic atomic sieve on top of a sturdy, traditional plastic sieve. It gives it backbone.
Yes. By doing this, you are deliberately sacrificing some performance. You only get about 60 to 70% of the theoretical permeance of pure, single-layer graphene. However, what you gain is instant, reliable manufacturability.
Oh, that makes a lot of sense.
You can take this hybrid coating process and roll it out on existing commercial hollow fiber or flat sheet membrane production lines, the exact same factories that make reverse osmosis filters for water purification today.
Yeah.
They bypass the manufacturing bottleneck entirely.
I have to point out one of the visual sources again here, the HelioGraph logo.
Right?
When you first look at it, it just looks like modern corporate branding. It's a dark blue background with a glowing light blue letter H right in the center. But when you look closely behind the H, there is this subtle gray geometric pattern. It's a hexagonal lattice.
It's very specific.
It is. That isn't just a random sci-fi texture. That hexagonal honeycomb literally represents the chemical structure of the carbon atoms in the graphene sheet. It is a literal diagram of a carbon honeycomb catching the universe's most elusive element.
It's a very elegant visual distillation of their core intellectual property.
Okay, so the physics of the hybrid graphene sieve are sound. The molecular geometry works. But I'm looking at this from a data center manager's perspective. You have a room full of massive, incredibly hot server racks pushing out exhaust that is full of vaporized thermal paste, dust, and electrical ozone.
Yeah, it's a harsh environment.
If I just spray that hot, dirty exhaust straight onto an incredibly delicate nanometer-thick sheet of engineered carbon, I feel like I'm going to rip it to shreds or at least clog all those microscopic pores immediately.
Your intuition is spot on, which is why you never expose the graphene membrane directly to raw server exhaust. Transitioning this from a material science lab into a functional piece of industrial equipment requires heavy preconditioning of the gas.
Okay, so let's describe the four-stage recovery process from exhaust intake to purified helium output, because this brings us to the core of what they call the helium recycler pod.
Exactly. The pod is designed to achieve a 90 to 97% total system recovery per operational cycle, and it outputs helium at an astonishing 99.99% plus purity.
That level of purity is military grade. So let's walk through these four stages, tracing the gas from the moment it leaves the hot servers to the moment it goes back impure. Stage one has to be dealing with the dirt and the heat, right?
Stage 1 is indeed the pre-filter. The helium exhaust venting off the computational racks is hot, ranging from 40 to 80 degrees Celsius, and it is heavily contaminated.
With what?
It carries airborne particulates, microscopic oil aerosols outgassed from the server components, and ambient moisture. As you deduced, if this mixture hits the nanopores, it causes catastrophic fouling. To prevent this, the gas is first routed through a graphene aerogel pre-filter.
An aerogel, so an incredibly lightweight, porous material designed to trap all the macroscopic garbage, the oil, and the dust.
Yes.
But filters clog. In my house, I have to throw away my HVAC filter every 3 months. In a 100-megawatt data center, swapping out massive aerogel filters constantly would be an operational nightmare.
Which is why the white paper details an incredibly clever thermodynamic loop to solve the clogging. Let's detail how graphene aerogel filters regenerate using captured data center waste heat.
Yes, how does that work?
Think about the broader facility. A data center is already generating massive amounts of waste heat, which is carried away in its primary cooling water lines. The HelioGraph system taps into that loop.
Oh, smart.
It diverts 20 to 50 kilowatts of this waste heat, which is sitting around 40 to 90 degrees Celsius, and uses it to literally bake the aerogel filters.
So every 4 to 12 weeks, instead of throwing the filter away, they just route the hot water from the servers to heat up the aerogel, vaporizing all the trapped oils and moisture and venting them away. The filter cleans itself.
It is a brilliantly elegant closed loop. By scavenging the facility's existing unavoidable thermal waste for the regeneration cycle, the net energy penalty for maintaining the pre-filter is effectively zero. They are using free thermal energy.
Okay, so after stage one, the gas is clean. No oil, no dust. But it's still hot. You still can't push 80-degree gas into a membrane without warping the polymers, right?
Right. Thermal expansion would distort the nanopores.
Yeah.
So, stage 2 is the heat exchanger. They route the clean gas through a heat exchanger connected to the facility's chilled water loop.
Okay.
This drops the temperature of the gas stream from roughly 70 degrees Celsius down to a perfectly stable 25 to 35 degrees. This cooling process has a secondary benefit, too. It forcefully condenses out any residual, stubborn moisture that survived the aerogel.
So now we have a gas stream that is clean, perfectly dry, and temperature stabilized. Now it's ready for the main event.
Stage 3 is the multi-stage graphene membrane array. This is the heart of the machine. The gas is forced through 2 to 4 sequential stages of the hybrid graphene oxide membranes we discussed earlier.
The chain link fence.
Exactly. The helium atoms, driven by Knudsen diffusion, easily permeate through the nanopores. The larger molecules, the nitrogen, oxygen, and carbon dioxide that leaked into the hull, are physically rejected by the lattice and vented out of the system.
And how much does that catch?
This primary separation stage alone achieves 85 to 95% recovery of the helium.
That is incredibly efficient, but 95% pure isn't 99.99% pure. If you keep pumping 95% pure helium back into the server hall, over time, that 5% contamination is going to build up and degrade the thermal conductivity of the room. You have to polish it.
And that leads us to the final step. Stage 4 is PSA polishing and recompression.
What is PSA?
PSA stands for pressure swing adsorption. The highly concentrated but not yet perfect helium stream is passed through a bed of molecular sieves. These are typically composed of a highly porous mineral called zeolite 5A, or sometimes specialized activated carbon.
Okay, I want to unpack pressure swing adsorption because adsorption with a D is different from absorption with a B. How does the zeolite actually polish the gas?
Adsorption is a surface-level phenomenon. Think of the zeolite as a microscopic mineral sponge, but it only works when you squeeze it. In PSA, they take the gas stream and highly pressurize it inside a vessel containing the zeolite.
And the pressure does what?
Under high pressure, the chemical structure of the zeolite physically traps the trace impurities, the last bits of nitrogen or oxygen within its microscopic cages using van der Waals forces. The helium, being inert and tiny, just flows right past the trapped impurities.
So the pure helium exits the vessel, but now your zeolite sponge is full of trapped nitrogen.
This is the swing in pressure swing adsorption. Once the vessel is saturated, you simply drop the pressure. Without the high pressure forcing them into the cages, the impurities release their weak chemical bonds, and the zeolite exhales the waste gas, which is vented away. The bed is instantly clean and ready to be pressurized again.
That is fascinating. You literally squeeze the gas to trap the dirt and let go to clean the sponge. So out of stage 4 comes 99.99% pure helium. And then finally, low-power blowers recompress that purified gas back up to the specific operating pressure of the data center hall, completing the loop.
That is the complete 4-stage architecture.
Well, let's detail the engineering specifications for blower power and containerized system footprints, because our visual sources provide an incredible perspective on the physical reality of this equipment.
They do.
We have a high-res photo of the deployed system. You are inside a hyper-modern data center. You can see the sleek black server racks secured behind an isolation wall, and sitting right there on the polished concrete floor is a standard 20-foot shipping container.
That it doesn't look like a standard container.
Not at all. It doesn't look like a rusty box off a cargo ship. It has been customized with large, transparent glass observation panels. Inside, you can see this incredibly dense, complex array of gleaming stainless steel pipes, analog pressure gauges, and the stack filtration banks. It literally looks like the engine room of a spacecraft.
What is remarkable from an industrial engineering standpoint is the density. That single 20-foot containerized footprint can process the helium exhaust for a data hall, drawing 5 to 10 megawatts of IT load.
That's a lot of power in a small space.
It requires minimal floor space, which is critical because square footage in a data center is incredibly expensive real estate.
And the electricity required to run it is shockingly low. The white paper highlights the power draw of the blowers. Because helium is so incredibly light, it is 8 times lighter than air, with a density of only 0.164 kilograms per cubic meter. The blowers circulating this massive volume of gas only require 2 to 5 kilowatts of electrical power per megawatt of IT load.
I'd take it a step further. It isn't just about weight. It goes back to the dynamic viscosity we discussed earlier. Because the viscosity is so low, you experience very little pressure drop across the membrane arrays and the piping. It takes a vanishingly small amount of kinetic energy to move it through the 4 stages.
Let's use an analogy to visualize this mechanical advantage. Pumping air through a complex filtration system is like trying to violently suck a thick, dense milkshake through a tiny coffee stirrer.
Right.
Your jaw muscles, the blowers, have to work incredibly hard, pulling huge amounts of energy just to move a little bit of fluid.
Exactly.
But pumping helium through the recycler pod is like drinking plain water through a massive, wide boba tea straw. There is almost zero resistance. The gas is so light and slippery, the internal fans barely have to spin to push it through the aerogels, the membranes, and the zeolites.
It's a perfect synthesis of aligning the fundamental physical properties of the gas with the mechanical design of the recovery system.
So we have established that the tech works on a molecular level. It's practically invisible in terms of power draw, and it fits neatly into a shipping container. But wait, we are talking about custom-engineered nanoporous graphene, multi-stage zeolite beds, and military-grade purity outputs.
Which usually means expensive.
Exactly. In any normal industrial context, that screams astronomical, multi-million-dollar R&D price tag. Data center operators are notoriously ruthless about keeping their capital expenditures, their CapEx, as low as possible. How on earth does a standard data center afford to buy this?
Well, let's analyze the financials, the return on investment, and this unique HIYS business model. Because the financial model presented in the white paper is arguably as innovative as the membrane itself.
Okay, let's hear it.
They baseline their analysis on a standard 5-megawatt AI data center facility. Under normal operations, without any recovery system in place, a facility of that size is spending between $500,000 and $1.5 million annually just purchasing replacement helium to top up what leaks out.
Just a continuous operational hemorrhage.
Precisely. Now, the capital expenditure, the cost to physically build and install the helium recycler pod for that 5-megawatt load is estimated between $78,000 and $195,000.
Wait, really? That's it?
Yes. When you model the gross annual savings against that CapEx, the payback period is astonishingly brief, between 0.6 and 3.4 months, depending entirely on where current helium prices are sitting.
Less than 4 months to completely pay off a piece of heavy industrial infrastructure. That is completely unheard of in data center construction, where payback periods are usually measured in years.
It is entirely unique.
In their base case model, assuming a helium price of $600 per MCF, that 5-megawatt facility yields $2.76 million in gross annual savings. But let's summarize how helium price volatility directly impacts the payback period for facility owners.
You have to run a strict sensitivity analysis because, as we established with the closure of the Amarillo Reserve, helium prices are notoriously volatile.
Right.
But the downside risk is incredibly insulated here. Even if the global market completely crashes to a highly pessimistic floor of $200 per MCF, which is essentially the baseline marginal cost of pulling it out of the ground, the payback period for the pod is still under 13 months.
Which any CFO would still sign off on instantly.
And conversely, during the current spot market spikes, where supply chain disruptions send prices leaping over $1,000 per MCF, The system pays for itself in roughly 3 weeks. The fundamental economics are structurally favorable, regardless of how the commodity market fluctuates.
But the white paper outlines a strategic alternative to direct purchase, and this is where the business strategy gets brilliant. Let's compare the helium recovery as a service model against traditional equipment purchase.
Right, the HEIS model.
Yeah. Instead of the data center writing a $195,000 check out of their CapEx budget to buy the pod, HelioGraph shows up, installs the equipment, maintains the aerogels, and operates the software entirely for free. Zero upfront cost for the data center. In exchange, HelioGraph meters the recovered gas and takes a 40 to 50% cut of the financial savings.
This is a masterstroke for accelerating commercial adoption. Let's discuss why the helium recovery as a service model attracts long-term corporate contracts. If we synthesize the underlying psychology of a data center operator, it revolves entirely around mitigating risk. Data center managers loathe volatile commodity markets. They hate unpredictable operating expenses because it ruins their profitability forecasting.
They want to know exactly, down to the cent, what their cooling is going to cost them for the next 10 years so they can price their server leases accordingly.
And the HIAS model delivers exactly that. It transforms a highly unpredictable, radically spiking helium top-up cost into an entirely predictable, zero CapEx efficiency upgrade. It perfectly aligns the incentives of the technology vendor and the facility operator.
Makes sense.
The more efficiently HelioGraph runs the system and the more gas they save, the more money both parties make.
It completely bypasses the data center's internal CapEx approval process, which can sometimes take a year of board meetings just to get a signature. You just sign it off as an operational expense reduction. But AI data centers aren't the only places venting this gas. Let's analyze the return on investment for data centers versus natural gas plant retrofits. This brings us to our third visual source.
Yes, the other photo.
It is a photo of another containerized skid, but the environment is entirely different. This one is outdoors, sitting at a massive, sprawling natural gas processing plant. It's surrounded by towering steel distillation columns, miles of heavy-duty piping, and glaring floodlights.
Quite a different vibe.
Totally. The container itself is painted in industrial gray, sitting on a reinforced steel grate. There is a worker in a hard hat and high-vis gear manually adjusting a massive mechanical valve on a pipe stenciled with the words helium product. It looks rugged. It looks like traditional heavy energy industry.
And that rugged deployment represents an attack on the absolute source of the global supply problem. Remember, approximately 75% of the world's helium is produced as a byproduct of natural gas processing.
Because they've been trapped in the same underground geological domes for millions of years.
Correct. The challenge is concentration. Many massive natural gas fields across the globe have helium concentrations below 0.5%.
That's so low.
It is. Economically, if you want to extract that 0.5%, you have to run the entire massive volume of gas through a full cryogenic separation plant. Cooling all that methane, nitrogen, and carbon dioxide down to near absolute zero just to isolate a tiny sliver of helium is financially ruinous.
It takes too much energy.
Consequently, these plants simply vent the helium. They throw it away into the atmosphere because they can't afford to catch it.
So how does the HelioGraph skid change the math for a natural gas plant?
They install their graphene membrane skid upstream before the gas reaches the cryogenic stage. They pass the raw, low-concentration natural gas through the nanopores. The membrane pre-concentrates the dilute helium, bringing the stream from 0.5% up to anywhere between 10 and 40% purity.
Wow, that's a huge jump.
Only then do they send this highly concentrated, vastly smaller volume of gas into the cryogenic plant for the final separation. Because the cryogenic Carbo expanders are now processing a fraction of the total volume, the electrical energy consumption of the cryo stage is slashed by 40 to 70%.
You essentially use the cheap atomic filter to do the heavy lifting, so the expensive freezing machine barely has to work. It makes the impossible economics suddenly highly profitable.
Exactly.
But let's contrast the return on investment. For the AI data center, the payback period was under 1 month. The white paper models the natural gas retrofit payback at 0.5 to 1.5 years. So data centers pay off faster, but what is the strategic global difference between the two deployments?
It is entirely about scale and impact. Deploying a pod at a data center plugs a leak in existing downstream demand. It's defensive. But deploying a retrofit at a natural gas plant unlocks entirely new, upstream, global supply. It is offensive. The white paper's financial models show that a single retrofit at a large natural gas processing facility could generate up to $90 million per year in net new helium revenue from supply that was previously completely stranded.
$90 million a year from a waste stream they were previously just burping into the sky. It is literally turning atmospheric pollution into a multi-million-dollar revenue stream.
It's incredible.
So the money is a no-brainer, and the tech clearly works on molecular level. But paper models and lab tests are one thing. How do you actually build a company that rolls this out to heavy industry? And realistically, what are the things that could cause this to fail catastrophically? Let's outline the aggressive roadmap for pilot testing and scaling commercial deployment, and then highlight the critical risks.
Sure. The white paper establishes a highly structured, phase-gated implementation roadmap designed to systematically de-risk the technology. Phase 1 is pilot validation, which spans months 1 through 18.
What's the immediate goal there?
The immediate goal is to deploy one single recycler pod inside a partner hyperscale data center and simultaneously deploy one slipstream testing skid at a natural gas plant.
So they aren't trying to sell 100 units on day one. What specific metrics are they watching during this pilot phase to prove it works?
They need to validate that the pristine laboratory data holds up in chaotic real-world environments. They are meticulously tracking the real-world membrane permeance over time. They're monitoring the fouling rates under actual contaminated exhaust conditions, and they're testing the durability of the graphene polymer bonds under extended thermal cycling as the servers spin up and down.
They need to prove that the magic sieve doesn't disintegrate or clog up after breathing hot server dust for a month.
Exactly the goal.
Yeah.
Assuming the pilot validates the thesis, they trigger phase 2, commercial scale-up, spanning months 12 to 48. This is the transition to modular factory production. The target is to manufacture and deploy 20 to 50 pods in the second and third years.
This is also the phase where they officially initiate the HRS model we discussed, right? Rolling out those zero CapEx contracts to lock in long-term corporate clients.
Yes.
And crucially, this is where they adapt those existing polymer membrane lines to coat the graphene rather than trying to build entirely new billion-dollar manufacturing facilities from scratch.
Leveraging existing industrial infrastructure significantly reduces their capital requirements and drastically accelerates their time to market.
That makes sense.
Finally, the roadmap outlines phase 3, ecosystem expansion, from years 3 to 7. This is the horizontal growth phase. They move beyond data centers and natural gas, expanding into semiconductor fabs and, fascinatingly, MRI hospital networks.
Oh, the hospital MRI application is wild. A lot of people don't realize MRI machines use powerful superconducting magnets that only work if they are submerged in liquid helium cooled to 4 Kelvin.
Very true.
The white paper details what happens during a quench event. If the magnet loses its superconductivity, the magnetic energy turns into heat, and the liquid helium instantly boils off, expanding at a ratio of 1 to 700. The machine explosively vents 1,000 to 2,000 liters of helium gas into the atmosphere through a vent pipe on the hospital roof to prevent the machine from exploding.
Which is incredibly expensive.
That is a $20,000 to $80,000 financial loss for a hospital in a matter of seconds. Putting a capture balloon and a recycler pod on that vent pipe would save medical networks an absolute fortune. Phase 3 also mentions they plan to physically build their own helium stockpiles to provide long-term price stability to their clients.
A very smart long-term play.
But I want to look closely at the critical risks and mitigations section, because no physical deployment goes perfectly according to the white paper. Let's highlight the critical risks. What is the single biggest technological risk to this entire enterprise?
Tech risk 1 is unequivocally membrane defect density. As we explored in depth, manufacturing pure graphene flawlessly is notoriously stubbornly difficult. If you have macroscopic tears in the atomic lattice during the coating process, you lose all selectivity. The nitrogen rushes through the gaps and the technology fails.
And how do they mitigate a manufacturing defect that occurs at the atomic level?
This brings us back to their core pivot, the hybrid composite architecture. By intentionally designing the system around the MPGO coating on a polysulfone support, they are accepting 60 to 70% of pure graphene's performance.
Right.
By accepting that lower efficiency, they gain reliable, repeatable manufacturability on existing polymer lines. They aren't trying to solve the perfection problem. They've engineered a system that functions brilliantly despite the imperfections.
Tech risk 2 is the fouling from the server exhaust we talked about, right? The vaporized oils, the dust, the ozone.
And their primary mitigation is the robust graphene aerogel prefiltration in stage 1. Intimately combined with the automated waste heat regeneration cycle. The system is designed to trap and incinerate the contaminants long before they ever reach the delicate separation membrane.
Okay, let's look at market risk. This is a big one. What if the data center industry just stops using gas entirely? What if the chips get so hot that they completely abandon ambient cooling and shift entirely to direct-to-chip liquid cooling, pumping chilled liquid directly through cold plates mounted on the processors? If they don't use gas, the pod is useless.
It is a highly valid strategic concern. However, if you look at NVIDIA's own published thermal management roadmap, it clearly shows that hybrid liquid and gas systems will remain the dominant architecture for the 100 to 500 kilowatt rack densities.
Why is that?
Direct liquid cooling is incredibly effective at handling the localized, massive heat generated directly on the silicon die itself. But you still have ambient heat bleeding off the motherboards, the power supplies, the networking cables, and the secondary components in the hall.
You can't put liquid pipes on every single wire.
Exactly. You still absolutely require a highly conductive gas helium to manage the macro environment of the data hall. The two cooling technologies are inherently complementary, not mutually exclusive.
Okay, I have one final operational concern, and it gives me anxiety just thinking about it.
What's that?
You are proposing to literally insert an experimental filtration pod directly into the critical cooling loop of a billion-dollar AI compute cluster. If a simple blower motor dies, or a valve sticks, or the filter clogs faster than expected, you cut off the cooling flow. The AI servers would hit thermal runaway and literally melt their own silicon in minutes. How on earth do you convince a risk-averse data center manager to agree to that level of operational vulnerability?
That is the ultimate operational risk, and any system that doesn't account for it is dead on arrival. They mitigate this through uncompromising redundant engineering. The helium recycler pod features dual, fully redundant membrane skids and an array of automated, pressure-sensitive bypass valves.
So if something breaks,
If any single component inside the pod fails, or if it requires manual maintenance, the system detects the pressure drop and automatically routes the helium flow completely around the pod. It bypasses the recovery process entirely, but it maintains the critical pressure and cooling flow back to the servers. Zero downtime maintenance isn't a luxury feature. It is the foundational design requirement.
so the servers never stop breathing. In the worst case scenario, you just temporarily stop cleaning the air while a technician swaps out a part it fails safely.
Exactly. It prioritizes the survival of the compute cluster over the efficiency of the gas recovery.
Bringing it all together, the roadmap is highly aggressive, but the risks are deeply meticulously calculated. And they are heavily mitigated by the fact that they are utilizing existing industrial supply chains. They are using commercial blowers, existing polymer housing factories, standard maritime shipping containers, and standard zeolite minerals.
They aren't trying to reinvent every single wheel from scratch. They are simply inserting one microscopic miracle material into existing, proven industrial plumbing.
It really is a textbook example of modular, pragmatic engineering. They are solving a highly complex macroscopic supply chain problem with absolute microscopic atomic precision.
Totally.
So, to summarize the massive scope of what we've unpacked today, we have a finite element, helium, whose very atomic structure dictates that it is bound to escape the gravity of the Earth. It is skyrocketing in price due to geopolitical supply shocks, and yet it is fundamentally thermodynamically required for the heat management of an artificial intelligence boom.
Yeah.
And we have HelioGraph stepping into this crisis with an elegant, atom-thick engineered solution, a solution that pays for itself in a matter of weeks, fundamentally turning a massive data center vulnerability into a profitable, closed-loop asset.
It fundamentally rewrites the thermal economics of the artificial intelligence industry and simultaneously offers a lifeline to stranded heavy industrial supply.
You now understand a hidden physical layer of the AI revolution that almost everyone completely misses. The next time you read a headline about a massive new supercomputer facility being built, you won't just think about the billions of transistors on the chips. You will think about the invisible, highly conductive gas keeping them alive, the microscopic geometry of the seals trying to hold it in, and the single layer of carbon honeycomb working tirelessly to trap it.
It does leave us with a much broader, almost philosophical concept to ponder as we wrap up.
What's that?
If human engineering can manipulate a single layer of carbon to trap and separate the second smallest element in the entire universe, it raises a profound question. What other so-called waste streams in our technology, in our heavy industries, or venting into our atmosphere are actually just incredibly valuable resources waiting for the right molecular filter? Are we rapidly entering an era where there is no longer any such thing as industrial waste, but only a temporary failure of separation technology?
That is an incredible paradigm-shifting thought to leave on. Maybe everything we are throwing away today is just waiting for a better, smaller sieve. Thanks for joining us on this deep dive. Keep questioning the invisible systems around you. And remember, the next time you see a helium balloon slip out of a kid's hand and float up into the blue sky, that's not just a balloon. That's a tiny piece of the AI revolution, gaining kinetic energy and escaping the Earth forever. See you next time.